Okay. So the third session, we will discuss about facility location problems. Previously, we already uh, in touch a little bit on how Excel solver to solve mathematical programming's problem. But those problem is considerably basic problem that we normally discuss during operation research class as an introduction for student that just uh, uh, just started learning operation research, and then there is linear programming inside that operation research topic. For this one, we will step a little bit more on the application of those mathematical programming in assisting decision maker on their facility location decision, or it's sometimes known as location science. There is a field for that one also. Okay. We will cover some basic facility location problems model, in which we have four basic location problem model here, covering problem, center problem, median problem, and fixed charge facility location problem. I said this is a basic facility location problem since whenever you whenever you're going to implement this type of models to analyze the real case problem, most often you will see is already being modified to suit with your real case problem needs. For example, if your problem consider one constraint that very specific for that problem. For example, okay, my facility have different way to address the coverage, for example. Okay, and perhaps you can start from the basic problem, and then you can modify it based on those basic those specific needs for your modelings. Okay, so my approach is to introduce you to the basic problem first, and then uh, for the final project, you can extend from this basic problem to be uh, implemented in a real case, more real problem that may happen in practice. Okay, the course outcome is from CO1. So for this session, I think we will discuss more on the theory first, and next week we will try to solve and using I think mathematical programming software, so that we have hands-on experience on how to solve this type of problems. And for start of the discussion, I try to find a good YouTube videos. Perhaps we can use this as an introduction to today's session. But for this one, because it's taken from YouTube, I will stop the recording first before share the screen to you. Okay. Yeah. Uh, I think that's a good introduction video about the perspective on how do you locate your facility, in this case a warehouse. The case that they discuss is from Sydney, Australia, and one key points that is mentioned from the video, that uh, an important factor is to know where your customer is, and to approximate the facility that you are going to use or build should be consider the proximity to your customer base, so that the serve to your customer should be optimal. And in this session, we will discuss several other factors as well. But what the videos mention, the factor that mentioned in the video is perhaps one of the main consideration. Okay. First, here we will start from one of the most popular facility location problems, in which it's called covering problem. Okay, the context of covering problems is sorry. Start first by discussing how do you define the terminology of covering. Okay, where in this context you define a facility here represent. Let me zoom in a little bit. Yeah. Okay. Okay. Here you define a facility. Here, sorry, the square with yellow shading here represent the facility. Okay, and the circle with gray shading with number 1 until 7 represent the customer. Okay, the terminology of covering or a facility could cover the customer here defined by the how the distance of the customer to the facility, the nearest distance from the customer to the facility is less than the coverage radius. Okay, so in this case we use the covering terminology. So we meet the terminology of the nearest distance. So for this example, the nearest distance perhaps a straight line connecting those 2 points. For example, from B to customer number 7 will be represented by straight line from B to 7. But for other case in perhaps more realistic or practical application, it may not be represented by straight line. Perhaps it can be a path from 7 to B should be through one road, something like that, or an indirect path. For example, there is no path from 7 to B, you should go to 6 first and then go to B. But most often it can be the covering is represented by the shortest distance. So if the shortest distance should be indirect approach, so those are the relative comparison to the coverage radius to determine whether it's in coverage or not. Okay, and okay, here okay, the notion of coverage I already explained here. Demand points or demand nodes said to be covered by the facility if the shortest path distance between those demand nodes to the facility is less than the or equal to the coverage distance. Okay, and then in covering problem, we will discuss a class of model or a class of problem in which we want to find the facility or to locate the facility that cover some area or some demand nodes in which we want to how to say, to cover all those demand area with as less facility as possible. Because the illustration is like this. If you want to open or use a facility, there should be a resource allocated to those facility. Okay. The more facility you use, the more resource you are going to need. Okay. And then in other sides, you have several set of demands here. Okay. Several demands that you need to serve. Okay. Now, the question is, let's say here you have another facility, okay, with its own coverage area. And now if you want to find the minimum number of facility to be allocated or to be used so that all the demand is covered by those facility, which facility you will use, okay? That problem is addressed as covering problem. In particular, we call it set covering problem. Okay, set covering problem. And this problem is very, very popular, and then sometimes it is the basic of many other modeling techniques in several more complicated problems. So it's good to start from this one. But the application itself is not only in facility location problem. For example, if for a facility location problem, you may find the application in locating ambulance facility. Perhaps if you want to make sure all your area is in undercover the ambulance facility, it means you first need to determine the radius, the minimum radius to be covered by the ambulance, for example, that one. And another one is police station to cover all the area. Where should you put those facility? Or it can also be a health facility. Okay. Now I think in 2020 until nowadays, I also see several papers being published on discussing about how to the most effective way to allocate the health facility, since there is a surge of needs of health facility, in particular for handling the COVID situation. And not only about facility, but this covering model can also be applied for crew scheduling problem, because crew is a resource, right? Resource need to cover several, schedule is the demand, something like that. So you can make it as model it as a covering problems, but it's not solving facility related problem. Okay, and next here, okay, I think you already get used to it right now, to seeing those mathematical formulation. For set covering problems, the steps that we did is basically the same with any mathematical modeling approach. We will try to define the input parameters, the decision variables, the objective function, and how do we define the constraint in mathematical formulation. Okay. First of all, we need to understand that the objective of set covering problem is to find a minimum cost. So the minimum cost of allocating facility that covered that make sure all the demand at least covered by one facility. Okay, so here to know which demand can cover which facility, we need to find an input or calculate input or parameters so-called AIJ that represent the adjacent metric, or a matrix that how to say, give you information about facility will able to cover a demand nodes or not, based on the coverage radius that we discussed earlier. For example, if you have a facility, let's say A, and then demand node 1, okay. Let's say we have the coverage radius is C is equal, coverage radius is equal 11. If the distance from A to 1, the shortest path, is 10, so the input parameter Aij, A, capital A, to represent the facility, the demand node. So so 1, A, this is the demand nodes, and J is A, is because this is a facility. Okay, A1A is equal to 1 because it's less than 10, the distance. Less than 11. The distance is 10, less than 11. So the value Aij is equal 1 to represent that the candidate site J, in this one is candidate A, can cover the demand nodes I, because the distance is less than the distance radius, that is the minimum distance radius. Okay, but what if the value of, let's say you have another point here, this is 2, and the value here is 15. What is the value of A2? What do you think the value of AA2? Jeremy, perhaps? Or Ivy? Or Joshua? I don't know who are still listening. Anyone? Okay. A2 should be equal to 0 because 15 is greater than 11. Okay, so that's the how do you understood the Aij matrix, or the parameters for Aij. And then for the cost itself, because we want to minimize the cost, we will need data related to, for each facility J, how much cost is associated with it. Okay, if you have the same cost, perhaps this one is not necessary. But if one facility is more expensive than the other facility, for example, if you have A here and B here, and both of them cover, let's say, the same demand nodes, and the cost of A is 100 and the cost of B 200. So of course you want to select the A facility instead of B, because when you're using A, you can cover all the demand, but with less facility cost. Okay, so this is important. But if this value is the same, it's 100 and this is also 100, so basically you will have, for this case, two optimal solution. You can select B to be open or A to be open. The cost will be the same. Okay. Next, the decision variables. The decision variable is simple. Xj will be equal to 1 if you select facility J or you utilize facility J, and otherwise it will be valued 0. Okay, and based on that, that information, you can formulate the objective function as mentioned here. You want to find the minimum cost of a set of facility that is being open or being used to cover all the demand, at least one. Okay, so here we have the formula. sigma j element j, it means for all the facility, this can be values 1 or 0, right? So for all the facility that open will be 1, right? And then you multiply it with the cost and you sum all of it, you will get all the facility costs here. It's pretty simple. Okay, and for the constraint here we have the constraint that each demand should at least covered by one facility. So here, this one Aij represent whether if you open facility J, right, one, this information will give you which node, which demand node I is covered by those facility J. And by checking all the demand nodes, then you check the sum of Aij multiplied by Xj greater than equal to 1. It means that you make sure at least for each demand node, you will have a facility assigned to it. Okay. For example, if you draw the image here, A and B. Here, demand 1, demand 2, demand 3. Okay. Okay, let's assume that all is connected and all Aij is equal 1. So if you have the Xj here equal to 1 and you multiply it with the Aij here equal to 1, so if you already covered this with the facility Aij Xj multiplied by Aij, the value will be already greater than equal to 1. So you will not have to open the B facility here if you already covered the demand nodes here. But if let's say the facility A is only covered node 1 and 2 here, like this. So the model will push you to open facility B to make sure node 3 is being covered by at least one facility, because here we don't have the connection from A to 3. So here Xj, Xb equal 1 should be open to make sure when we check the demand node 3, it will covered by at least one facility. Okay, so that's the constraint number 2. And the last one is just an integrality constraint to make sure that the decision variable will be in the value of a binary variable, in which should be equal to 1 or 0. Okay, I will start a little bit detail in the first model, but for the second and the third and the following model, because we will like reuse some of the constraint, I will not explain it again in detail. Okay, so for the first one, I try to give you all the detail and the basic understanding, so you will not miss any point about the constraint, objective function, decision variable, and input parameters. Okay, up until this point, any question that you would like to discuss? Okay, not yet. Okay. Okay, so perhaps I can continue. Okay, yeah. Next, let's try to use those model and implement it in a very simple example of set covering problems. Okay, first we see that we will have a set of demand nodes I and J, right, in the general models. And in practice, the demand nodes I and the facility or candidate facility J may or may not be the same nodes. Okay. For example, the one that I drew earlier, I always separate. This is A, this is B, this is the node 1, this is the node 2, 3. But in some case, the facility can also be the demand nodes. Okay. So for example, here, A and B also are demand nodes. 1, 2, 3 can also be a facility. Okay. And that might happen in practice as well. So for this example, we will use this kind of assumption where the candidate facility and the demand facility can be uh, selected from the same point. So you will have set I will be equal set J. Okay. Then you can see the example in figure 2 on the top right of the slide. Uh, Here we have A, B, C, D, E, F. Okay. And not all nodes is connected to each other, but here you can see the connection. From A to D is 10, A to B is 8, A to C is 15. Okay. Um, Here, for this problem, uh, if for a set covering problems, first, yeah, you already define the network and then the set of facility and candidate facility. And here we know the distance from one node to another nodes. But for a facility, set covering problem, the parameter we need actually is whether one facility can cover another facility or not. The parameter that I mentioned earlier, or we denote it as AIJ, or the adjacent matrix, is not yet available here. We cannot see from the picture. Okay, so first, to define the AIJ, we need the variable related to the variable that mention the coverage distance. So it means that if you if you use one node as the facility, based on this coverage distance radius or coverage distance units, you can you can generate information of the AIJ, in which it will define which nodes will be covered if you open in the facility in that particular node. For example, if you use A as the facility here, and we know that the coverage distance is 11, so here you need to check whether which node is covered by A. For example, A to D, the distance is 10, and 10 is less than 11. So D to A is equal to 1 because it's coverage by A. And then B, here is 8, so it's coverage. So here the AIJ is equal to 1. And then here 15, it's greater than 11. So AIJ here is 0. Okay, and so on. After here, see, what about E? We don't have the connection here, but remember the coverage distance is measured using the shortest path from those nodes. For example, if you want to connect to E from A, perhaps you can use from A to D to E or A to B to E. Okay, sorry. So based on this information, you need to check the shortest path. Here we have 21 from A to E, 10 plus 11, 21. Okay, 21. Here we have 18 plus 24. So 21 is the smallest, and it's clearly not connected. It's clearly greater than 11, so it's not connected. Okay, repeat the same process to generate the Aij matrix. Then you will get this matrix that you need for the modeling parts. So you have the distance based on the shortest path, and then you get the adjacent matrix to be used later in your model. Okay, then based on this general model, you have fj multiplied by xj. Here, what is the value of xj? It is mentioned that the cost of using each facility is equal to 1. So the total objective that you want to minimize will be 1 multiplied by xa, whether it's open or not, plus 1 multiplied by xb, and so on until xf here. Okay, and then for the constraint, you have here, right? Aij multiplied by xj greater than equal to 1 for all I. So first you will need to check for all I here. Node A covered, node B covered, node C, node D, node E, node F. Okay, for each of those customer node, you will need to check which facility is covered that A nodes. You can use this adjacent metric. So for A nodes, if A is the demand, so it can be covered from A, B, and D. So XA plus XB plus XD greater to equal to 1 to make sure the node A is covered. And you repeat the same things here. If you want the node B is covered, so XA, XB, XD. It accidentally it happened to be the same set of facility. And then C is equal CEF. So XC, XE, and XF. Okay, repeat the same process until F. And the last one is for the integrality constraint. Okay, that's the way you formulate the mathematical model for this particular problem. Okay, but later when you use mathematical programming tools like AMPL or others, you don't have to decompose the model like this. You just need to write the same way that you write the general models, and it will be easier instead of breaking down one by one the model like this. But for Excel problem, Excel solver, this kind of decomposition may be necessary before you able to solve it. Except you using like VBA programming approach in the Excel, you can make it, you can decompose it using programming approach. But if you are not using that kind of help, perhaps you need to write it, decompose it this like this before you can use the Excel solver. Okay, yeah, that is the example. I will not demo the way we like what we did last week for using the Excel solver. I can leave it to you as an exercise. And how do I get this solution is I will explain to you later. There is several ways to get the solution, but this one I use the ample programming, mathematical programming approach, and that one we will learn next week. But the results shown that basically you need only 2. Z equal to means that among these 6 facility, you only open 2 facility so that it cover all those nodes, all those demand nodes. Okay. And here to show you the final answer is, let's see XC. Okay, if you open XC, and then XD, and then XF, you will able to cover all the demand nodes. It means like XD will cover, let's say, A, B, and D, and E. And then XE, wait, XD, yeah, XC will cover the here and here. Okay, sorry, this one should be 0 because it's only 2. Yeah, so you need to open 2. This should be 0. It's wrong, typo. XC and XD is enough to cover all the demand nodes. Then you get the minimum cost for cover all the demand nodes that are available in your network. Okay, that's the beginning, the first model that we are going to discuss. After this, it will be a little bit faster because I don't have to explain more detail on several repeating constraints. But before that, I think I will take 5-minute breaks and we can use this as a discussion. Okay, we'll stop it first here. Perhaps if you have any question, you can ask me directly. I will still listening to the audience. Okay, now that you know how to model one set covering problems, well, set covering problem is one of the basic, right? Another variance of set covering problem, which still basic, also is now known as the maximum covering location model. So what is maximum covering location model? Well, basically, in set covering models, we have an assumption that all the all the demand should be covered by at least one facility. Okay, but in this model, we want to show you that uh, if you find an example from a real case situation, for example, perhaps in real case situations, you may not be able to, to allocate that many facility so that all the demand can be covered, right? It happens in practice. For example, let's say your company have limited budget, okay, limited budget, or there is like limited option to open the facility. So it comes out that you can only open several number of facility. Let's say one facility only or two facility only based on the 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 initial findings. Okay, based on budget, based on several things, you can open only one or two or a number of particular facility. So in this case, you need to redefine the problem, right? Reformulate the set covering problem. And this one is already addressed by some researcher, and they call the model as the maximum covering location model, in which what we try to uh, uh, try to optimize here is we still try to maximize the sorry earlier we tried to minimize the number of facility being used, right? The cost, the minimize the total cost of facility. But for now, because we know that we can only use a number of facility, in which we will define as P, number of facility. And also we assume that we have the information about in each demand how many number of demand we are going to solve or to serve in that particular nodes. It can be defined as like the more the demand, the more prioritized it needs to be solved. It needs to be served. Okay, so now the objective is changing to when the decision is consists of first still locating the facility, which facility you will use, but now the facility that you select should be aimed to maximize the demand being covered, because not all the demand can be served. So you need to considerably select which facility that you use so that it can cover the most demand or the maximum demand out of those facility. Okay, well, based on that description, we need to formulate the set covering problem into this maximum covering location problem. Okay, first you need to have another information, uh, demand at each node. Okay, or you can treat this one as the weighting factor of each node. If you have the same demand for each node, it means it has the same weight or the same priority to cover those demand. But if one demand is more prioritized than the other, so you should try as much as possible to cover those demand, right? For example, in the real case, perhaps you have one location have more customer than the other location. So of course you want to, if you have an if you face by a condition where you cannot serve all the demand, of course you will prioritize the demand that has more customer or more weight or more priority instead of the other one. Okay, that kind of problem is addressed here. And the input should be we should have this kind of input, hi, which is the demand associated with each node I. Okay, and another one is the number of facility that can be located. Okay, it's p. And we have an additional decision variables. We still have the same decision variable with the previous one, which is xj, where equals 0 or 1, in which it's equal 1 to represent facility J is being selected, and 0 if not. And we have additional variable Zi to show us whether the demand I is covered or not. Okay, because we want to maximize all the demand being covered, so we need to see which demand is, whether that particular demand node is being covered or not, and we need to introduce additional variable Zi. Okay, and the objective is maximize hi multiplied by Zi. Hi is the demand, Zi is 1 or 0, and the constraint, okay, for this one, aij multiplied by xj is actually to make sure the one particular I, right, is being covered, right? So when you use the same formulation and then put the variable zi here, so it will restrict the zi will be equal to 1 if you are allocating the facility that covered those I. For example, if you have x a here equal to 1, yeah, and then it's cover here the z1. Okay, so z1 will always be equal to 1 if you have this aij here equal to 1. Okay, this is the constraint to make sure that one. And then, okay, this to make sure or to populate this zi, if it's being covered, it will become the value will be 1. If not, it will be 0. And for this one, total xj being used should be less than equal to p. P is the number of facility that is able to be allocated. For example, you can only use 4 facility. So total xa plus xb plus xc, something like that, until xf should be less than equal to 4. So you can only select 4 out of, let's say, 6 facility being available as a candidate. Okay, and the last one is just the integrality constraint to make sure that the value of z is equal 0 or 1. It means that it's a binary. Okay, next, yeah, the same way we can represent this one. With the same example, we can put, let's say, we need to put more information like the demand here. And then another information is how many facility can be open or can be selected. We know from the set covering problem that with 2 facility open, with p equals to 2, all the demand can be covered, right? So let's say, what if we can only open 1 facility out of these 2 facility that can give you optimal solution? Well, by using the maximum covering location model, we can use the same approach. Let's say if we have the covered distance is same with the previous one, so we'll still have the aij matrix, adjacent matrix equal to the previous example. Then we need to break down all the constraint, in which now we have here, because we want to maximize the demand being covered in each facility, so we will need to multiply 10, because the demand in A is 10 multiplied by ZA plus 8 multiplied by ZB. Z represent whether facility A being covered, sorry, demand node A being covered or not. This one is 0 or 1, right? And then we repeat the same formulation until XF. So 10ZA plus 8ZB plus 22ZC here plus 18ZD plus 7ZE and plus 55ZF. Okay, this is the decomposition of this constraint. Sorry, the formula. And then for this constraint, okay, well, we can break down as with the same way that we break down the constraint that in the set covering problem, xa plus xb plus xd. But here, instead of 1 or 0, we put za. Okay, so whenever this one is equal to 1, either any of this is equal to 1. Let's say this one equal to 1. The value of ZA cannot be 0. Should be at least 1. What if this one, 2 of this is open? 1, 1, 1. Because this one is greater than, so it means that 2 greater than equal to 1. It's still feasible, right? But if you put here all is 0, XA, XB, XD is 0, right? This is 0, 0, 0, less than. This cannot be equal to 1, should be equal to 0, because the value is either 0 or 1. Okay, that's how they formulate the to make the value of Z to represent whether it's being covered or not. If it's covered, so it should be 1, if not, should be 0. Okay, the same way here for all of the nodes. And another additional constraint is sum x j equal j element j xj, right? So xa plus xb plus xc plus xd plus xe plus xf less than equal to p. P here is equal to 1. Okay, and based on this, you can see that the solution, the optimal solution will be you open node C. Why? Because you can see here, C has 22 here, here is 55. If you select another node, here 1 and here 1, this will be violate this constraint because you can only open 1. So if you open XA1 here, 10, and then 8, and then 18, it's less than 84. So that one is not better than opening the C. Okay, so this one will be the optimal one. Okay, up until this point, are you still following the model? It's still very, very, very simple. So I think you can straight implement this in Excel solver. But again, whenever the number of nodes will be grow larger, the decomposition will be so difficult, so many constraints that you need to decompose, and it's heavy workload to use Excel solver to solve that one using if you want to decompose it one by one. Okay, and then okay, one particular characteristic of covering problem is actually whenever you increase the number of facility, okay, the number of facility that can be located, it means the number of P from whenever you increase the characteristic of set covering problem, it is normally that you will have reached at certain point, certain facility, the number of demand covered will be 100%. Okay, sometimes for this one, let's say 19, right? Sometimes it less than 19. For example, here the number here already 100, something like that. So let's say if you already get the 100% in 7 with 7 facility, it's useless you allocate more facility, right? It's just increase the cost of use more facility, or yeah, it will ask you to allocate more resource if you use more facility. But if your objective only to find the maximum demand coverage, so you need just to find the optimal number of facility being located. Okay, so if it is already 100%, it cannot be grow more than 100%, right? So sometimes the experiment being done in the analysis of this model is just to find the optimal one, the optimal number of facility being allocated. And the same way, whenever you increase the number of facility being allocated, the incremental demand coverage will be less and less and less until the increment is so not significant, so that you may want to stop increasing the number of the facility, because the benefit that you get by adding more facility is not significant to the it's not adding more facility is not significant to benefit that you want to get, in this case incrementing the demand coverage. Okay, and then for solution approach, okay, there are several solution approach that you can consider, but for this one, I think we will discuss only one, because for this, the rest of this will be how to say, for example, for heuristic, there is so many heuristic can be applied for this type of problem, but I think we will see if you somehow later working on this particular problem for your final assignment, there we will discuss the heuristic approach for the specific type of problem, for covering problem, for example. But if not, I will just try to introduce you how to implement those mathematical modeling approach in, let's say, AMPL approach, because the Excel software, I think you already understood how to use it. Okay, the last part for this one is, yeah, here are some references about how this particular model is being applied in practice. I have found the paper from even in the 70s, and it is still relevant even until the recent paper like 2015 or even 2020. There are still people using the covering problem to solve their real case problem, but of course with some additional modification. Okay, yeah, I will take a rest about 5 minutes, but before that, do you have any question that you would like to ask? Okay, as you can see that covering problem is quite restricted, set covering problem in particular. When you face a real case problem, perhaps it may not be as directly, it will be not directly fit with a particular model. In this one, we want to show you another example of a constraint that you might, or a consideration that you might found in practice, and then we will see that covering problem is not suited for that model, and then we will see that what kind of modification necessary from those particular set covering problem to make into the problem that we are discuss. Okay. The problem that we are going to discuss here is known as center problem. Okay, center problem is considering, we can say that, let me address this one. Okay, it considering to minimize the maximum cost between the client and the closest facility networks. Minimize maximum cost. So there is two word that normally separated, combined in one sentence. Minimize maximum cost. It means like when you allocate one facility, you want to make sure that the coverage for the furthest demand from that facility is the minimum among all those possibility. Okay. Okay. Let's start from this one. set covering problem, when you relax the total coverage requirement, it means that when you don't have to cover all the demand, it becomes the maximum covering location problem, right? And if you relax the coverage distance, it means that, okay, where we consider that whenever we allocate one facility, for example, okay, this is the facility. Let's say we'll allocate this one, okay? Here, the distance is, let's say 10, this 15, this 22, and going here is 33, okay? So the minimum, the maximum distance among all this demand is this one, right? The one that has the poorest service is this one. Let's say this is the ambulance facility here. So if you go to this, if you want to serve this distance, they need, let's say this one is 33 minutes before arrive here. So this guy that live here is get the worst services, right? Okay. But compare this one to you decide to allocate here the other nodes, the other facility instead of the first one. Here, let's say here. This one you equals to 1, okay? Let's say here is become 5, here become 22, here become 27, and this one become, let's say, 30. Okay. So now if you select this one as the facility, the furthest distance coverage of the customer that has the poorest service is this one, because the distance is 30, right? If you want to serve this customer, the distance is 30. So you compare those two options. Okay, if I open the facility, the first facility, and then compare to open the second facility, you will select to open the second facility because the minimum of worst service is this one. 30. Yeah, 30. Okay, that's the how we understood the center problem. Okay, so that's why it's often called minimax, and it's a little bit more complicated than the set covering problem. And later you will see the modeling approach. And normally this kind of model is used to represent service that is critical to emergency critical service like emergency services and fast response services, something like that. Okay, or even sometimes communication network, I also find this kind of modeling approach. Okay, but since it's derived from set covering problem, so many of set covering problems application can also find in the center problem application. Okay, now the modeling part. Okay, for center problem, actually there is two category of center problem. There is a vertex center problem, in which the facility is located at the vertex. Vertex mean the nodes, right? So for example, if you have like this, you have A, B, C, D, E. The facility location should be selected from the vertex. Okay, but if you have but there is another facility location model which called the arc P-center model, in which the facility are allowed to be selected or to be allocated in the arc. For example, here, the model will be much different from this one, but we will not discuss that in this particular session. But if you are interested in that model, perhaps we can discuss it, perhaps maybe for your final project or other type of project. It's okay. But for now, we stick to the easier part first. Let's discuss the vertex P-center model. Okay. Okay, for this one, we still use the same input parameters, I, J, because we want to minimize the maximum distance coverage. We need the data related to distance from demand node to facility, Dij. And then we also need the demand. Wait, I think the demand is not used here. Sorry. So the demand is, this one is not necessary for P-center. And then P is the number of facility to be located. The decision variable is, we still use the same one, xj, to represent whether we want to allocate the candidate in facility J or not, and yij to, this one, the new decision variables that is introduced for P-center model. So yij here represent the fraction of demand at node I served by facility J. So it's like a percentage of demand. Let's say you have here 10 demand. Here you allocate xj here, xj equal 1. This covered here and here, right? For example. And based on we don't have the aij here. So let's say for this one, we cover yij, let's say 50%, 0.5. Okay, so the rest 0.5 we can cover from another part, something like that. But those are only additional decision variable to help you calculate later something that we call W, in which W represent the maximum distance between a demand node and the nearest facility to that demand node. Okay, and the objective function is to minimize this W value. Okay, because like the previous example that I mentioned. Okay, if you allocate the facility here, the furthest demand, the furthest demand coverage is this demand nodes with 30. But if you allocate here, it's, let's say 33. So you select this one. This will be the W. This W1, W2, something like that. Okay, but we will select the if we will compare if this one is less than this one, so the W will be 30. This one should be replaced by the new one. Okay, and next here we have the constraint yij is equal 1. Okay, this is the percentage of demand coverage, right? For each demand, okay, for each demand node, we should make sure that the total facility, the total facility that cover those demand in node I, the total demand being covered should be 100%. So it's equal to 1. Okay. And the total facility xj should be equal to P. Previously we have less than equal, right? But for now, since we are not going to minimize the total facility, but we want to have exactly P facility, so we put equals P. And for constraint number 4 is to make sure that the demand being covered in I should can only be covered in I if we have the facility located in J. So it means that the value of Yij cannot be more than 0 if we don't have the facility located in J. Okay, so it will be relative to J. Okay, and then the constraint number 5 is used to calculate. Okay, here we will calculate, we will see all the demand nodes, and then we will check the furthest distance covered by those the nearest facility located to that particular demand. Okay, and then we compare all those facility all those distance, all those nearest distance, and then we take the biggest one. So W will be always greater than all those Dij multiplied by Yij. Okay, and then you will get the value of the furthest demand coverage. Okay, and then the rest is just non-negativity constraint and also the integrality constraint. Yij equals greater than 0 and xj is equal 0 to 1 is only binary. Okay, and using this formulation, you will able to get the W. So it will be the minimum farthest distance coverage from the facility that you selected. Okay, and okay. For the solution approach, again, it always have like this heuristics and then exact solution. Why? Because most of the problem that we discuss here is either NP complete or NP hard. What is NP complete and what is NP hard? We will discuss that complexity theory in the week 6, I guess. The 6th week of our class. That complexity represent how difficult the problem is how difficult the problem being solved. Okay, if you have an algorithms that can solve the problem in, we call it polynomial time. It means that we can measure the time to solve those problems by a particular algorithms that frankly said is fast. Normally we don't really need those meta heuristic or heuristics approach. Okay, and whenever you find problems that is NP complete or NP hard, later on we will discuss a particular set of algorithm called meta-heuristic approach that is normally used to attack or to find the solution for this particular problem. Okay, and for this one, since heuristic will be, we will find heuristic approach in every type of problem, and each heuristic normally have their own rules. So that's why I'm not discuss that particular uh, algorithms for each problem, because again, uh, that kind of method will be, we will have so many variation of those model. So I guess it is better we determine what kind of problem we are going to discuss for the final project, then we will study in more detail during your project assignment. But for now, I will just teach you how to use a more generic solver that can be applied for any type of problem that can be modeled in a mathematical way, like using Excel solver or using Ample, or later on a little bit more robust, but it's still considerably able to solve NP hard or NP complete problem. But we can learn this problem, this solution, and it can apply to many type of optimization problems. So that's why this I select to teach you this type of approach. Okay, center problem. Yeah, this is the last one. There is several since center problem is more complex than set covering problems. I found that there are several newer references for this problem. And as you can see, the approach is not only using mathematical programming or exact approach. Sometimes we will find like this one, B colony optimization is a meta-heuristic approach. Variable neighborhood search is a meta-heuristic approach. Tabu search is a meta-heuristic approach. Okay, something like that. That's the topic for I think after midterm. Yeah, after midterm we will discuss about those meta-heuristic approach. Okay, let's have 5 minutes break. If you have any question about the center problem, you can ask it now, please. Okay, that's about center problem. The last, no, not the last. There is two more. Next problem that we are going to discuss is so-called median problem. So those previous two models, the covering problems, the center problem, is mostly discussed about covering or providing service to the customer, and um, the service is measured based on the distance and the amount of demand being served at those customer. And but for median problems, we are more concentrating on the relationship between the distance and the facility that is going to serve those demand. Okay. For example, if you have a problem of locating, let's say, warehouse of this or distribution center, and for this one, we are going to focus on, okay, if I want to allocate the warehouse at some location, the important factor that we are going to consider is perhaps the how far is the distance of this warehouse that I locate to the customer that available in surrounding those warehouse. The other point that being important factor is how often or how many demand are being covered at those particular location. Okay, if your model are concentrate on those two important factors, then perhaps your the approach that you're going to use will be median problems. So basically, it's selecting the facility locations that is going to minimize the total demand multiplied by the total distance covered, they utilize to cover those particular customer. Okay, um, you can see the model here. Uh, we can utilize the same notation like demand or distance. Demand here, hi for each node, distance from one node to another nodes, and the number of facility being located. But since we now fully consider that one particular demand point can only be served by one particular demand point can only be served by one facility. So we want to make sure that there is a variable that take account of those condition. We call it here Yij. It can be only 1 or 0. It will be valued 1 if the value of the if the demand at the nodes I are served by the facility at nodes J. Okay, so this is the additional constraint introduced for P median. Okay, for the objective, we want to minimize the objective, the demand at that particular nodes multiplied by the distance, multiplied by whether those demand is covered by a particular facility J. So since we make sure already only one facility can cover demand nodes, so this will make sure that the distance will be only one arc will be take account for each pair of facility and demand nodes. Okay, and then to make sure that constraint, one facility can only serve by one demand can only serve by one facility. Here we need to make sure all element I should be sigma j for all element Yij should be equal to 1. Okay, it means that only one particular j can we serve the each customer node. And this constraint is still the same, sigma xj equal p. And this one is to ensure the relationship between Yij and xj. It's like the value of Yij should only be 1 is if we have the xj equals to 1. If the xj equal to 0, so the value of all the Yij should be 0. Okay, for those particular j. Okay, and this one, wait, w, well, I think this one, we may or may not need this one, but what is w? Yeah, I think we don't need this one. Okay. And then xj, yij is element 0 or 1. It means that it's a binary variable. So like it's here, 0 or 1. Okay. And next. Again, for the solution approach, there is several solution approach that you can follow. In particular, this one we will learn after the midterm. This one I will cover if you use this problem as your final assignment. But if not, perhaps I will just leave it for the independent learning uh, for each of the students. And next week we will discuss how to implement this MPOL for each of these location problems. So, and median problems also similar with the covering problem, center problems. There is several recent research discuss the median problems, still discuss the median problems and still applied for the recent problem happen in practice. Okay. Next, perhaps this is the last problems that we are going to discuss related to facility location problem. It is called a fixed charge facility location. Okay, basically it is a variance of median problem. In median problems, we take account the demand multiplied by distance multiplied by the whether those the demand multiplied by distance for each the nodes that is being covered by each facility. But for this one, we also take account the cost of utilize those facility. For example, if you want to use a facility in city, let's say A, to cover demand surrounding there, you will compare to facility located in B. Okay, surrounding here. Median problems only take account of the demand multiplied by the uh, uh, distance here, right? This one, this one, this one, this one, right? But if you remember that for covering problems, we also take account the cost, fixed cost here, and fixed charge facility location problems, combining those two consideration. You take account of the fixed charge facility location cost and also the demand multiplied by distance in terms of cost. Okay. So here in fixed charge facility location problems, we will consider two decisions in which we want to minimize the cost of utilized facility and also minimize the transportation cost. Okay. Normally, the more number of facility that you allocate, the more fixed charge here, the blue part you will use. But the more facility you use, maybe will reduce the total traveling cost until at some point the decrease of facility the transportation cost is not significant, so that the saving of um, those uh, those adding more facility lead to a higher total cost. So what you are going to find here is the number of facility that give you the minimum total cost based on the total travel cost and the total fixed cost used by using uh, 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 the facility. Okay, and the model is formulated as follow. First, we will use again the fixed cost of using facility from the set covering problems, and we use the same median parameter that used in the median problem. And now we need another variable to convert, because distance multiplied by demand cannot be sum with the fixed cost of allocating facility. So you need to use a cost per unit distance per unit demand. So perhaps like, let's say 10 kilometer distance of transporting one unit product is equal to, let's say, 10 pesos, for example. So it will be multiplied by alpha is equal 10. Okay, those are the parameters that is needed here. And for the decision variable, basically it's the same with p medians. Okay, xj, yij, it's all the same. And even the objective function here, this part is the same with median problem. But we have an additional multiplication with alpha to convert this one into a monetary measurement in terms of cost. And then this one is from the set covering problem that represent the fixed cost of allocating facility. Okay, and the rest, this one, this one, this one, is equal to the constraint that we use in the p median problem. Okay, and sorry, this should be yij element 0 or 1. Okay, yep, that is the fixed charge facility location problem. Yeah, perhaps for many paper that is available in the recent study, they will consider fixed charge facility location problem instead of those p median, p center. P center may be sometimes because it's different with those two, but instead of set covering and p median, we will mostly found this fixed charge location problem instead of those two. Okay, yeah. Yeah, as you can see here, we can still see several reason paper related to facility location problem. And now there is even more extension on this fixed charge facility location problem, like considering green or sustainability or environmental factors, and many other extension. Okay, I think that's all about the uh, the model and the facility location problems for today. And it's already 9. Anything else you want to discuss before we close the session?
Sir, where do you upload the recordings?
Oh yeah, the PowerPoints will be on the Blackboard, but after I finish the recording of this slide, I will put it also in the YouTube channel, in the description in the YouTube channel.